Hi everyone. In this video, I'm going to show you how to interpret and analyze simple graphs and how to draw a graph for a given story or create a story given a graph. So this is a fairly standard introduction to graphs at a lot of different levels. And the first graph I have for you guys is a climatograph, is what it's sometimes called, for Red Deer, Alberta. And so there's two different things measured here. On the left-hand axis, we have temperatures. So these are temperatures, and they're in red, which is conveniently color-coded for the line graph. And on the right-hand side, we have precipitation, which is how much rainfall there is. And of course, this is in metric because anyone uses metric these days. And the black line going across the graph is freezing. All right, so 0 degrees Celsius is the freezing point. Okay, so there are various questions we could answer about this data. What is the warmest month in Red Deer? Well, the warmest month in Red Deer is going to be the peak of the graph, and that is the 7th month, which is July. What is the coldest month? Well, the lowest this graph goes is in the 1st month, which is January. So January is the coldest, July is the warmest. What month do they have the most precipitation? Well, they actually have the most precipitation also in July. If you look across this, the peak of the precipitation graph is 90 millimeters in July. We could also just get specific months. Like they say, April showers bring May flowers. So how many flowers do they have in Red Deer? I guess we'll look at their April showers to figure that out. In April is the 4th month. So this is April. And if we read across, the value for precipitation should be, sort of about here-ish. So if this is 15 and this is 30, that's about 2/3 of the way up the box maybe, right? So if we sort of split this box into thirds, you're going to get 20, 25, and 30. So there's about 25 millimeters precipitation in April. And knowing Red Deer, that's probably not all rain either, which doesn't bode well for their flowers. I say this in Calgary where it's slushing outside right now in May, so maybe I shouldn't be saying anything about Red Deer's weather. But anyway, there you have it. So this is how you can interpret a graph. You can read values off of a graph by taking a value and reading it across to your relevant axis. And I chose this graph because it's a double axis graph, which is about as hard as it gets in terms of axes. Our left axis here tells us temperature. So this tells us May, which is the month when I'm recording this. The average temperature in Red Deer is 10 degrees Celsius. Cool enough, you probably still want a jacket. And it only warms up at peak to about 16 degrees in July, which is pretty cool. And their average temperature in December is, I don't know what that is. That's sort of between 10s here and 15s, negative 15s here. Maybe that's negative 13, negative 13 and a half. That's pretty cold in January. And December is not much better. December, if we read all the way across, remember we have to go to the left axis because it's temperature. That's, negative 12 maybe. And so that's how you can interpret graphs. You take the graph, you measure to the axis, and it can tell you various things. Often you care about the peaks, which is the highest points. You care about the troughs, which are the lowest points. And you can read values to your axis carefully and get an estimate of the actual value. Of course, you can get better data with an actual table of values, but graphs are nice for giving us all of the data at once in an easy to understand format. The next thing I want to show you guys is how to create a story to go along with the graph. So this is a distance time graph, and I need to come up with some sort of story. So let's take a look at this graph and see what we can figure out. And then based on this, we're going to need to come up with a story that models this situation. So wherever this is, they're starting at time 0 with a distance of 0. Okay, so that's, I guess, pretty standard. They're starting where they're starting, and I guess this is distance from where they started. That's pretty cool. They go out at a completely steady pace, actually, because it's a straight line. They get somewhere and they realize, I need to turn back for some reason. Okay, so they turn back. They go from distance, just shy of 2, back to a distance of about 1-ish. And then at distance 1, they stay for a little while. And then they go much faster. Like this is much steeper, right? Until they're distance 5 away. And then they stay at distance 5 for a while. And that's the end of our data. So I need to come up with a situation where someone wants to go away from their destination, double back for a while, and then just chill. And then boodle it, twice as fast-ish until they get all the way to the destination. Actually, that's much more than twice as fast. If we actually figure out the slope, this is a 4 distance in about 1 time. So this first piece is about 2 distance in about 2 time. So if we divide that, the slope here is 2 distance in 2 time. This is 1 distance per time. And I don't know what my distance units is or my time instance is. And then this one here is 4 distance in 1 time. So they're actually going 4 times faster. Okay, so why would someone want to go 4 times faster? Okay, so here's my story. My story is, I think it's because of the weather. I'm inspired by the slushy, awful, cold weather we're having. So I'm going for a walk, and I leave my house, and I'm going just for a nice, gentle walk. I'm walking away, and then I see off in the distance some dark, looming storm clouds rolling in awfully quickly. And I passed a shelter back at distance 1. So I decide, you know what, I'm just going to walk my way back to that little shelter, and I'm just going to stay there until the weather passes. So I get to the shelter, it's starting slushing, whatever, it's getting uglier and uglier, and you know what, the weather is actually looking worse and worse, and by this point it's slushing and raining and it's terrible out, and I'm like, you know what, I just need to get to where I'm going. I'm going to my friend's house to play some Xbox, right? That's what you guys play these days. So I'm going to race to my friend's house. Wait, you guys play Xbox on live, don't you? Okay, whatever. We'll just pretend that you actually sit with your friends and play Xbox. So I'm going to race. I'm going to run as fast as I can to my friend's place to play Xbox. Whew. I ran there 4 times as fast as I was walking before because I wanted to get out of the slushy, awful weather as long as I could. And then I just stayed at my friend's house waiting for the awful weather to pass. Okay, there's my story, and I'm sure it's relatable to you guys because I put in regular, teenage activities like Xbox. Awkward pause. Okay, and we can also do the reverse. Here's a story, and we're going to turn this story into a graph. So Mr. Armstrong left his home and walked to the train station. He waited a few minutes for the train, then got on when it arrived at the station. On his way to the next station, he realized he forgot his bag at home. Oh no! So Mr. Armstrong got off at the next station, had to wait a bit for a return train. Then he rode the train and then ran back home. I guess because I'm late. Once he found his bag at home, he realized he didn't have time to ride transit, so he drove to his destination. Sketch a graph to model Mr. Armstrong's distance from home. Okay, so let's do the same thing here. This is my distance. This is my time. Okay, so let's label these different sections. He left his home and walked to the train station. Let's call that our first interval. So walking to the train station, probably not that far, probably pretty slow. So this is going to be my first time interval. When I got to the train station, I waited a few minutes for the train. Okay, so that's me waiting for the train. Then the next thing I did was I rode the train to the next stop. Now, this is probably faster than walking, right? I don't know about you, but I can't walk as fast as a train. So I'm going to show this as fairly steep because the train is going much faster than I can walk. So that's my interval 3. And I only go on for 1 stop, so it's not going to be very long. Then I realized I forgot my bag at home. So I wait for the return train for a little bit. Then I ride back to the previous station. Let's do this color. So ride back to the train station is 5. So riding back to the train station, probably about as fast. So you'll notice that the steepness of this graph is about the same as the steepness of this graph because presumably trains are the same speed. And then I ran back home. So I probably ran about twice as fast as I can walk, right? Oh, I'm not leaving my colors down here. So this is 5, this is 4. Okay, now we're up to 6. So 6, let's see. So here it took me, I don't know, however long that is. I need to do about half of that. Let's say I can run twice as fast as I can walk. So now I'm back home again. Okay, now it takes me a little while to find my bag, probably not that long. Once he found his bag at home, so that's finding my bag at home. So here we go, there's 7. And then I drive to my destination. Now driving's probably about as fast as a train, I would think. So I'm going to sort of match the steepness of this graph, going all the way to my destination. Let's say my destination is here, and that is interval 8. Okay, and then presumably I'm at my destination for a while. I don't know what I'm doing there, but I guess I'm staying for a while. Okay, so I've just taken this story and turned it into a graph. And I don't have any, you'll notice I've got no numbers on this. I've got no time, I've got no distance. The numbers I don't really care about. The point is, can you figure out what it means to go up or down a graph and the steepness of a graph and what a steepness of a graph means for your data? Okay, cool. I hope that was helpful for you.